So I don't have any particular announcement to make. I'm sorry that I uploaded the lecture 7 so late on Friday. There was a technical problem, so I uploaded a version that then was without audio, so it was useless. Yeah, given that, so let me know if you have questions. So we can start from, let's say, lecture. I guess last time we discussed lecture 4 in detail. So is there any question? We can sort of proceed in order. So do you have any question about lecture 4 or previous lectures? Great. Any question about lecture 5?
I have one question. When you talk about the structural instability or stability,
yes.
You say that when beta is equal to 0, there are oscillations, right?
Yes.
And you talk also that there is an structurally unstable.
Yes.
But my question is, that means that it's marginally stable?
Yes, so let me describe. That was, I think, in lecture number 6, but we can go ahead with that. So, so the equations we were considering were Lotka-Volterra equations, and in particular, after the usual rescaling that we do, we obtain u dot equal to u 1 minus v minus beta u, v dot equal to v 1 minus u. Okay, can you see it? Great. Now, if beta is equal to 0, what we discovered is that there are oscillations of predators and prey. Okay, so if you look in phase space, we have something like this, and we keep oscillating. Okay, and here there is the fixed point 1, 1. This is if beta equal to 0. Okay, and if beta equal to 0, this fixed point, as Ivana suggested, is marginally stable. Okay, so this fixed point is marginally stable. What does that mean? Is that if I look at the fixed point, again, in the case beta equal to 0, if I look at the linearization around the fixed point, and I look at the eigenvalue of the linearizations, the real part of the eigenvalues is equal to 0. Okay, this fixed point is called marginally stable, which means that if it's not unstable, in the sense that if I perturb it, I will not move away from it, but it's not stable in the sense that I will not go back. What happens is that if I move away, I'll stay in the vicinity and I'll oscillate. Okay. In that case, I'll oscillate, but I will not move far away. So that's marginally stable. Now, one question, which is actually in a way very deep, is so this is the marginal stability. Now, what we obtain is that when we look at beta larger than 0, okay, we discover that this fixed point becomes stable. Okay, so if beta is larger than 0, if it is not too large, so let's say if beta is between 0 and 1, as sort of discussed on Slack also. So if beta is larger than 1, but is larger than 0, but lower than 1, this fixed point here, which now is u star equal to 1 and v star equal to 1 minus beta, becomes stable, right? Which actually is globally stable. So doesn't matter where you start, you're going to end up there. Okay? So the fact that these results hold only when beta is equal to 0 is called structural instability, which means that basically I'm finding this property, in this case oscillations, but then as soon as I introduce a parameter, no matter how small it is, I will end up with a completely different dynamical behavior. So Ivano's question is the, I mean, if I understand it correctly, is this point structurally unstable because it's marginally stable? So are these two things deeply connected in some sense? And the answer is yes. So the reason why you have structural instability is exactly because you have marginal stability in some sense. So the point is that marginal stability is a scenario where these eigenvalues, let's say if we look at the local picture, these eigenvalues are equal to 0, and as soon as you change some parameter, you are gonna move these eigenvalues somewhere, right? So either they're gonna move to become positive or to become negative, but somewhere they gotta move, right? They cannot stay there. So the point is, we have here marginal stability is not a surprise that when we introduce some other parameters, we destroy it, right? And the reason is that when we set some parameters different from 0, in this case beta, the eigenvalue will move somewhere. And when they move somewhere, they're not going to have a real part equal to 0, likely. Of course, this is not a necessity. You can also introduce a parameter and they just change their imaginary part. But it's not a surprise that you destroy this behavior. Or to say in the more global picture, we say that in this case, we have a quantity which is conserved. So we have an energy which is conserved, whose derivative is 0. As soon as you introduce some parameter, it's very likely that that is not going to happen anymore, that you will have some dissipation, right? And therefore, that the function that was sort of flat during the dynamics now is going to change over time. And in fact, we didn't see it in class, but if you take the same function v here, which was u minus u star log u plus v minus v star log v. Okay. If you take this function here, in this case you have dv dt equal to 0. If you plug exactly the same function and you calculate the derivative over time here, what you're going to end up with is something like minus beta u minus u star squared, which is always negative, right? So you see that there is a quadratic term that appears, and this term has a beta in front, okay? And if beta is equal to 0, this is 0. If beta is different from 0, you have this concal, right? So you can play with it. Right? Does that answer your question, or I take a long route that didn't answer it?
No, it's right. I have another question, and it's about what you comment in the Slack about a third point,
yes.
a third stable point. I can see it. I don't know where is that third point.
Yes, I think it was a question by Paul. Who can I erase this part below?
Yes.
So he noticed that there are actually 3 fixed points. So there is the fixed point u star equals 0, v star equals 0, okay, which is always unstable. There is the fixed point u star equal to 1, v star equal to 1 minus beta, okay, which I'll tell you when it's stable. And then there is another fixed point, which is u star equal to 1. So you set this equation equal to 0. Sorry, u star equal to 1 minus beta. You want u star equal to 1 over beta, okay? And v star equal to 0. Okay, so if V star is equal to 0, this equation is 0. And if U star is 1 over beta, this is 0. And you see that this part here is 0. Okay, so you have these three potential fixed points. Now you immediately see that this fixed point exists only if beta is larger than 0. Otherwise, that fixed point is infinite. And this fixed point here is stable only if beta is lower than 1. And this is stable only if beta is larger, is lower than 1. Okay? Is larger than 1, sorry. Okay? So if you take, oh, okay, so what kind of bifurcation do you have here? Do you want to guess?
Pitchfork.
No.
Um,
Well, there are no other possibilities.
Let me look.
Yeah, let's draw it. So you have U star. Let's look at the oh, actually, let's look at V star. It's easier, right? And here at U star as a function of beta. Okay. So let's look at V star as a function of beta. V star is 1 minus beta. So it's like this, and then it's this. Okay. Okay. So you have this fixed point here, and then this is the stable one, and here it's like this, and U star, it's 0 here. No, it's sorry, it's 1 here, and then it's something like this, which is this one, and then there is this one which is unstable, and this one which is unstable. Okay. So what's kind of, do you understand what this means?
Yes.
So you look at this star, you have two fixed points, 0 and 1 minus beta. And this is unstable below beta equal to 1, and this is stable above. Okay?
Yes.
And 0 becomes stable above beta equal to 1. And a similar picture is here. So what kind of bifurcation is this?
Transcritical.
Yes.
Yeah.
Yes, it's a transcritical bifurcation, right? It's a transcritical bifurcation with two species. We saw only the one with one species, but it's a transcritical bifurcation, right?
All right.
And what is the ecological interpretation? The ecological interpretation is that if the carrying capacity is very large, so this scenario here, basically the population of prey is limited by predators, so it's always equal to 1, and the population of predators is limited by what will be the carrying capacity of the prey, right? Somehow, and the terms that here are sort of hidden, which is the terms we scaled this by. On the other hand, if the carrying capacity is low, basically the predators don't have enough food in practice, and they go extinct always, independent of the initial condition, and you end up at carrying capacity.
And the curve of the space, of the phase space, are going to look like?
No. So in this case, since they
are going to.
Good point. So in this case here, now you have a stable fixed point, which is this one.
Yes.
Yes. And if you look at the trajectory of U star, what you're going to see is something like this.
And in the phase space, it's like they're going to be like a spiral, right? Oh. No.
Yes. They're gonna, I mean, it depends how big is beta, I think. I'm not sure if, I mean, there might be a critical beta over which you don't see anymore the spiraling thing. Because basically beta controls how fast you relax. Right? If you do the math, this thing behaves as e to the minus beta, okay, t. So if beta is large, you go very fast. If beta is small, you go very slowly. If beta is 0, basically you stay there. Right? Now, if beta is large, if 1 over beta is smaller than the typical period, you see that you're going to go immediately to equilibrium, right? It's like to say that you don't have time to spiral, right? You do something like this, and you end up there. So, how many oscillations depends on what is the period of those fluctuations.
Okay, thank you.
Other questions?
I have some questions about the Lyapunov function.
Yes.
I didn't understand how can we use it and
how can we
use it? I mean, how can we construct a Lyapunov function in general? And for the symmetric case, can we always construct a Lyapunov function in the way that you showed us?
The answer to the first question is I don't know. The answer to the second question is no. So let me go through it. So there is no way to no method to construct a Lyapunov function. So it's not that you give me nonlinear dynamical systems and I have easy condition to check first whether a Lyapunov function exists, and second a way to construct it, right? So if you give me let's say a 5-dimensional dynamical system, I cannot tell you in general whether it exists a Lyapunov function, and let's say that you also you know that it exists a Lyapunov function because you have found it. I don't have any method I can apply to find it. Okay, so it's really a matter of luck, dreaming, inspiration. There is no direct method to do it. And I mean, this is one, in some sense, actually this question came up in both the other Q&A, so I think it's a very good, I mean, it's something that you all ask. And another point which is important to mention is that Lyapunov functions are fundamentally different than potentials, right? So a potential, if you want, a potential is a very special case of a Lyapunov function. Okay? So if you have a potential, you have a Lyapunov function. But the other way around is not true. Is that clear? Right? Because if you have a potential, I mean, so if you have a dynamical system x dot I equal to fi x, I want to write it as minus dv over dxi, right? I can immediately check whether I can write it like this. How do I check it? Well, I have just to check whether dfi equal to dxj is equal to dfj dxi, right? Which these two corresponds to the second derivative of v. So if this is true, I can always build this, right? And I can build this. I know how to do it because I have just to integrate that. And if I can build this, I also can show that dv dt equal to the sum over I dxi dt dv dxi is equal to minus sum over I dv dxi squared. So this is a Lyapunov function. Okay. Right. So the potential case is this easy case. Now, one thing that is actually confusing for many physicists is that you have sort of the impression that the Lyapunov function is just a potential. That's not true, right? So the number of cases where you can build this is much smaller than the cases where you can have a Lyapunov function. Right? So the fact that you don't have this property doesn't mean that you don't have a Lyapunov function. For instance, the Lotka-Volterra equations we just brought with the beta larger than 0, they are neat a Lyapunov function, okay? But they cannot be written with a potential. It's easy to check. Right? There is another property, is that the potential, so a function that has this property, is unique up to the addition of a constant. Right? So you take a potential, the only transformation you can do is to add a constant, right? If you add a constant, it's still a potential. For the Lyapunov, if you have a Lyapunov function, you can take any function g such that the derivative is always positive, and you can check that if L of x is a Lyapunov function, then g of L of x is a Lyapunov function, right? And you can choose any function g which has this property, right? This is very easy to check because you can write dl dt. Sorry, let's call this g of x. The g over dt is going to be just the g dl dt. So if this is positive, right? If this is positive, doesn't change the sign of this. Right? So that means that if you give me a Lyapunov function, you can build, infinitely many Lyapunov functions, which are all deformation, arbitrary deformation of this function. Right?
But what do we mean saying g prime x greater than 0? Because
x here is its variable. So this is a scalar function. L is a
okay, okay,
yes.
okay.
Sorry, yes, I used the x in two different ways. Yes, this is a function of from R to R, right? So it's a one-dimensional function. But this means that if I, in principle, if I give you a nonlinear dynamical system and I tell you it exists a Lyapunov function, find it, it's possible that the 7 of us come with completely different functions, right?
And then in the symmetric case, you show that we can construct Ln Lyapunov function as the sum over E and J and some other things. But can we do this every time in the symmetric case?
For the Lotka-Volterra, yes.
Okay.
So for the Lotka-Volterra, you can check that that's a Lyapunov function, right? And
also in the case of S species that compete among. Yes. Okay.
Well, I mean, yes. Yes, you can do it. I mean, technically, I sort of hide under the carpet what happens with the species that are present versus the one that are absent, but yes, you can do it. In practice, it doesn't matter. So, but yes, you can do it for all these species.
And just another thing, yes. Can we have a Lyapunov function with more than one minimum?
Yes. This is something that a posteriori wasn't unclear from my video, but yes, you can have that. So you can have a function that always decreases over time but has multiple minima. And in that case, the Lyapunov function is still very useful because it tells you what is the Bayesian of attraction of this minimum.
Okay.
I mean, in that respect, it's the same thing as a potential, right? It's a quantity that only decreases over time. So if you start in some position, you can only decrease. So you're going to go to the local minimum in the same Bayesian of attraction. It's fundamentally different from a potential in the sense that you cannot generate the trajectories deriving that function, right? That the trajectories are not the trajectories that go in the direction of the gradient. You can do more complicated things, but you're going to still minimize it. So you can have a Lyapunov function with multiple minima, and what happens is that you end up in one of the minima. I think this was not clear from the videos. In the case of the Lotka-Volterra, that function is a quadratic form, so you have only one minimum by construction, which means that you are going to end up in one minimum. Any other question? No question about pesticides. That was surprising also today. No one seemed surprised about it.
I have a question about herd immunity.
Ah, okay. So
yeah.
let's before we move to that. So
okay.
Is there any question for lecture 6 or earlier?
Yeah, I have some question about the conservative systems.
Okay.
Because we have stated the theorem for two-dimensional conservative systems, and we have said that the energy E must be not constant in every open set. What do we mean?
I mean that clearly you can choose, if you choose E to be a constant function in some open set, it's possible that in that open set it doesn't change because the derivative over time of a constant function doesn't change. Right? The point is that you don't want functions that are constant in an open set. Right? You want functions that continuously change as you change parameters. Right? Otherwise, I mean, in 2D, so you can have directions that are like minimum, but that are not, there is not a bubble that you can construct and is constant there. So any, okay, so that's just mathematical jargon, if you, I mean, depends how you see it, but that's the proper definition. In practice, it means that you, if E, the energy is an analytic function, so all the derivatives are defined, right, and the second derivative, all the derivatives of any order are defined, that's equivalent to say that that function is not constant.
Okay.
So if you have a function which is smooth everywhere, which is what you always have, almost, that's equivalent to say that the function cannot be constant, right? Because if that function is constant, it's trivial that that function doesn't change during the dynamics.
Okay.
Right? Because I mean, it's constant, so.
Yeah.
Good. So if there is no, is there any other question on lecture 6? Okay, so we can move in the magic world of epidemiology. If you have, I mean, since I upload, I mean, the other groups, not everyone watched the lecture 7, of course, because I uploaded very late on Friday. So, I mean, I'm happy to answer questions, but yeah, I mean, I don't expect everyone to have watched it. So Federico, you had a question, sorry.
Yeah, so basically when we study herd immunity, we said, okay, we have the group of people which is infected and we expect to have a maximum in there. And then we have the recovered people and they will tend to R infinity. And we say, okay, the maximum will be when R0s is equal to 1. And that's fine because it's a solution to the differential equation. But then I have not understood when we have herd immunity. So is it when S is smaller than 1 over R0?
Depends, well, it depends on the initial condition, right? So that's actually one of the major confusions in 95% of the people that talk about herd immunity, and let me say 100% of the economists that talk about herd immunity. Sorry, this was easy. But the problem is that it depends on the initial condition, right? So if you are let's look at the infected over time. As you said correctly, well, this point is the point where the susceptible population is equal to 1 minus 1 over R naught. Okay. Now, the issue is that this is the threshold of any. Okay, so there are two things. So if you are in a situations where S of t is equal to 1 minus R naught, let's say that this is your initial condition. Okay, so let's say that you are in a situations where you are at this point. Okay, should you go out and party? Okay, this is the question. The answer depends on what is I of 0, of course, right? So how many people are infected around you? Right? So if I of 0 is much smaller than 1, well, it probably is better that you don't party for a couple of weeks. But still, if this number is very small, right, the likelihood that they are going to infect, I mean, let me say one note. This is if there was not stochasticity. Then we are going to see that this is not the case. But on average, let's say, if the number of infected people is very, very small, then it means that basically they are not going to find anyone to infect. I mean, they're going to infect less than one person, so the epidemics is going to run. Now, actually, let me say that in a different way. So let's say that you have a given I of 0, right? How many people how many people are gonna be infected as the time goes on, right? Well, these people are gonna infect on average less than one person because they don't have enough susceptible population, right? And this will go on. So basically, if you are here, whatever is this number, right? What is going to happen here is that, well, there's going to be some transient, but let's say I of t is going to be something after this point. I of 0 e to the minus 1 minus, let's say, what do I want to say? Well, it's gonna decay with some factor over time. Okay. Well, technically it's not like this because then also the number of susceptible diminish here, so it's different. But the key point is how big is this number, clearly, right? So if you start from a scenario where this number is very small, yes, that's true. I mean, if you start from a scenario where the number is very small, the epidemics is not going to spread, right? So if when you have this fraction of population which is susceptible, right, and this number is much smaller than 1, then the epidemics is not going to expand in the population, right? So the individual probability of getting the disease is very small, right? Even if, so if you are still susceptible and this number is much smaller than 1, it's very likely that you don't get it. On the other hand, if you are here and this number is fairly large, right? It's true that each of those people is going to infect less than one person on average, but still there is a large number of infected people in the future, right? That's the point, right? So, so you can check how big is this number, right? Sort of at least numerically, right? But it's not actually, well, if you put numbers, let's say if R naught is equal to 2, right? This threshold here is 0.5, right? But R infinity in this case is 0.8, right? So there is like 30% of the people actually get it after you reach this point, right? But the reason is because you have this sort of reservoir of infected people that can infect other people. Now, of course, they infect one person, I mean, on average less than one person, but still, I mean, in one generation, if they each of them infects like 0.9 people, it's going to be a bunch of persons that are going to be infected, right? Is it clear?
Yeah.
Now,
I still have to kind of internalize what we're studying, but I mean, I understood the fact that based on R0, we get a smaller number compared to R infinity, and therefore this is better because we are protecting some portion of population without basically doing anything, let's say.
Well, there are two things, right? There are two things. One is how an epidemics proceed, right? And the other one is what you do when you vaccine people, when you do vaccinations. When you do vaccinations, you do this scenario here, right? Because you, I mean, think about flu. What you do is you vaccine. I mean, in principle, in practice, it doesn't work. But let's take about measles or like all the diseases that are basically eradicated because we have vaccinations. You vaccinate a large portion of the population, a portion of the population which is larger than this, and you have very few infected around, right? Therefore, the epidemics doesn't spread, right? That's the trick, right? So you have 95, 98% of the people that are vaccinated against measles, and then you don't have epidemics of that, right? You don't have epidemics not only in the 95% that are vaccinated, but also in the 5% that are not. Right? Now, a different thing is when this I0 is much larger than 1. Right? So if I0 is much larger than 1, it's true that, I mean, you can have reached this threshold here, but still you have a bunch of populations that are going to be infected because there is a high number of people that is going to be infected.
Okay, so I mean, from the mathematical point of view, what is the definition of herd immunity? I mean,
the herd, okay. From the mathematical point of view, is that if you look at the RT for time going to infinity, this is lower than 1. Okay? That you don't infect everyone, basically. That's now, this is the definition. How many you infect depends on the initial condition, right? That's the whole point. Right? Let me say something about all this discussion. Now, in a few months, remember about this conversation we are having, when, I mean, hopefully in a few months, a vaccine is going to be available, right? And you are saying, yeah, we're going to go back, I mean, to normal life, etc., etc. Now, one thing that I'm sure we're going to discuss, I mean, I don't know if I'm recording, but okay, remember about this. one thing that are going to be discussed is that, well, perhaps we're going to be, I mean, if you are lucky, we are going to try to vaccine so many people, but we're going to have I0 that is going to be much larger than 1, right? So there is going to be the issue that, sure, we're going to vaccinate many people, that is going to be great, and many people that have not been infected are going to be vaccinated, but still we're going to have a large portion of the population which is going to be infected, right? And so, since we cannot vaccinate everyone, there are going to be many infections even after the vaccination. Right?
But
oh, well,
unless we vaccinate everyone, of course. If we vaccinate everyone, that's.
So you mean that we are going to reach the herd immunity before all go?
No, I mean, just to be clear, about COVID, we are here. Right? This is the whole issue. This is the whole issue why we are on Zoom, right? Is because we are here.
Okay,
in Italy, I think, I mean, I don't remember the exact numbers, but there was a survey, a serological survey, and I think we have about less than 10% of people that are recovered. So we have a small fraction of the population that had it, and yet we saw like, we have seen what happened in March and February, and the same applies to basically every country of the world. Right? So there are differences, but we are still in this regime here, right? And I mean, the proof that we are in this regime here is that I mean, we see everywhere that we have a second wave. A second wave means that you are still growing exponentially, right? So you are very far from this point.
So
my point is a different one. My point is that when we think about like vaccination for flu, for instance, we think about this regime here, right? I mean, for flu, we never reach herd immunity. We never vaccine so many people, but in principle, this is ideal, right? When you think about measles or all the fantastic success of vaccinations where we eradicated our disease, we reached this threshold basically, right? But we were in this condition. Right? The moment where the vaccine for COVID is going to become available, we are not going to be in this condition, right? So we're going to have a bunch of people that are infected, and they can infect all the people that are not vaccinated. Right?
But what if after the vaccination we wait we wait for E to decrease and then
that would be ideal.
Okay.
From an epidemiological point of view, but as you know, there are conflicting forces, right?
Yeah, of course. But I mean, what needs to be done is to vaccine all the people and then wait to EDT to decrease.
Well, I mean, the point is, it's a complicated question here, which goes well beyond epidemiology, right? So there is a trade-off of cost and benefits, right? So there is a non-trivial question. I mean, there is a non-trivial question: who do you vaccinate first, right? The most obvious answer is you vaccinate like the most fragile population. You vaccinate old people. And you vaccinate people that are essential. So you vaccinate doctors, nurses, and people that work in hospitals, right? So you vaccinate these populations because basically what you try to do is to reduce pressures on hospitals, right? Then, of course, you will not vaccinate younger people who are less likely to develop sort of bad COVID symptoms, but still they have a non-zero possibility, right? So this is one possibility. The other possibility is when you vaccinate people that are most likely to spread the disease, right? And if you have to vaccinate people that are more likely to spread the disease, well, that's not easy, right? Who you vaccinate? People that party a lot? That's a possibility, right? Kids, perhaps, right? Because kids typically transmit, even if for COVID it's weird, but they are very transmissive because they're very transmissive in their social groups, right? So there is a non-trivial strategy of I have, I don't know, I can vaccinate 40% of the population who I prioritize in order to save the greatest amount of lives, right? So it's not trivial. What I'm saying is, don't think that the moment where a vaccine is going to be out, that there is going to be herd immunity by vaccine immediately, right? That nobody's going to be infected. And the reason is that you're going to be you have still a bunch of people around that are infected. Right? So what is going to happen after the vaccine, if everything works nice, is that basically you take a bunch of people from the susceptible class and you move it from to the recovered class immediately, right? Just now, in principle, you would like to move all of them. Now, in practice, you cannot. So, yeah. Is that clear?
But from a mathematical point of view, if we vaccine, let's say 70% or the percentage of people needed to reach the herd immunity, and if we also have E of t, which is close to 1, then the curve of ET will decrease from this point, or?
Well, I of t will never be very close to 1, right? You'll never have all the people infected at the same time.
Yeah, but okay, let's say.
Yes, so what is, let's say, you have a bunch of people that are infected, you vaccinate 70% of the population. What happens is, well, first of all, it depends on where are the other 30%. Most likely, given the dynamics are going to be still susceptible because most of the people are susceptible. So what happens to the other 30%? That's the question, right?
Yeah.
Some of them are going to be infected. How many of them? You can solve the equation, right? So the equation is so you have that 1 minus R infinity is equal to S of 0 e to the minus R naught, R infinity minus R0, okay? So you say, let's say that the moment I have the vaccine, I vaccinate a fraction V of the population, okay? And I have I people that are infected. And also I have already a fraction R, which, let's say, are pre-vaccination, people that are recovered previously of the vaccination, right? So let's say that for simplicity, this R pre is much lower than 1, okay? So basically this, if this condition hold, this is 1 minus, this vaccine people is R of 0. So this time 0 is the time of vaccination, right? And then I have this I of 0, and then I have that S of 0 is just 1 minus I of 0 minus R of 0, which is B, right? So then you have to solve 1 minus R infinity equal to S of 0, equal to 1 minus I of 0 minus B, e to the minus R0, R infinity minus B. Okay? where this V is the fraction of people that you have vaccinated just after the people that you have vaccinated. We are working in the assumption when the population is there are not a huge fraction of people that is that has recovered, and there is a given fraction of people that are infected at that time. Okay. Then when you have to solve it, and you're going to find an infinity, and the number of people that have been infected after the vaccination are going to be R infinity minus V minus I of 0. Right? So these are the people that are recovered because they are vaccinated. These are the people that are recovered because they were infected the moment you did the vaccine. And these are the people that have been infected after. Right? We are working in this assumption, which is important, of course, but it's reasonable. So it strongly depends on what is this I of 0, right? Having a large I of 0 increase actually that number. I mean, it's not easy to see, but if you plug the numbers there, you can see it. Right, just to solve it numerically, put R not equal to 2, and you're going to see it.
Okay.
Right. I mean, in practical terms, the issue, this is well beyond the lectures, but in practical terms, the issue of the vaccine will be that there are not going to be doses. I mean, it's not that one day you vaccinate 70% of the population, right? I mean, it's logistically impossible to vaccinate 40 million people, let's say in Italy, in one day, clearly, right? So, I mean, the vaccination for flu lasts for 2 months, and there are much fewer people that get it every year. So it's going to last months, if not 1 year, right? Yeah. Well, I didn't want to sound pessimistic with this. Actually, I think that if there is a solution, is that one. But you have questions?
About the document of the declaration.
Yes.
I don't know. I'm a little bit confused if we are in like that part of the curve of the infected people. Why are they saying that in that declaration?
So let's do a poll. Who believes is a good idea and who believes is bullshit? So who believes is a good idea? It's a fine position. I mean, it's who believes is bullshit.
I think that does not need to be like too extreme. Like
Okay.
I don't know, a little bit of bullshit.
Okay. No. I mean, what do you think? I mean, what do you think? I mean, what is the problem of that strategy?
I think that speaking in mathematical terms, if we really can subtract these fragile people from S, it could be a good idea. But
let's speak in mathematical terms, right? So let's think that you can subtract. You can have like you can take this 40%. And you put them in some place, and they don't have contact with anyone else, right? Let's leave alone the fact that this is impossible, but let's assume that we can do it, right?
The problem, I think, it is that if these persons are a fraction bigger than the fraction needed for then the fraction that cannot vaccinate, or the fraction that stay out of herd immunity when we rejoin these two groups, the spread will.
That's exactly the point, right? The point, yes. So the point is, you have this fraction of the population. So after the spread, you're going to be at R infinity, right? For that restricted population, right? Now the point is, when you rejoin the two community, then the fraction of recovered people is going to be X times R infinity, right? And you can check whether X times R infinity is larger or smaller than 1 minus 1 over R naught, right? So at the end of the, let's say the first phase, right, you have the population and the fragile, right? At the end of the first phase, you're going to end up with some population that got it, which is R infinity, okay, of this point here, right? Now, let's say that this is a fraction X, which is 0.6, 0.60%. So you're going to start, when you join the two population, at an initial condition of R0, which is equal to X R infinity, right? So S of 0, so yes, so S of 0 is going to be equal to 1 minus X R infinity, right? And you want this number to be lower than 1 minus 1 over R naught. So you want 1 over R naught to be lower than X R infinity, okay? Right? So let's say that you take R0 equal to 1.4, okay? R infinity is 0.5, okay? So X R infinity is 0.3, and 1 over 1.4 is 0.7. Sorry, where are you? Right? So 1 over R0 is 1.7. Right? So in this scenario, doesn't work. Right? 0.7, sorry. Okay? So 1 over R naught is larger than this. So you're not able to contain. Well, let's try that R0 is equal to 2. Right? Perhaps we are in that regime. Well, if R0 is equal to 2, R infinity is equal to 0.8. So this, well, in this case, you actually X R infinity is 0.48, right? And 1 over R naught is 0.5, okay? So again, it doesn't work. I mean, this is very little difference, but still it doesn't work, right? Let's say that you are at R naught, which is very large. Let's say it's 5, okay? Well, here R infinity is basically 1, right? So here you have X, you basically have X, so it's 0.x R infinity is 0.6, right? But 1 over R naught is well, much smaller than 1 over 6. It's 0.2. Okay. So the point is, in the regime where R naught is very small, doesn't work. The regime where R naught is very large doesn't work. In the regime where R naught is 2, the 2 points are very close. But then, I mean, do you trust these? I don't know. I mean, if you want to be on the safe side, you want that this number here is much larger, right? So that means that, okay, you do all this game, assuming that everything before works, that you can actually isolate the people, then you open the doors, and then this is going to spread again among the population, right? This is, of course, in a very simplified scenario, right? So you are in a population that is well mixed, you don't have age structure, etc., etc. But if you want to have something convincing, it has to be convincing in this scenario as well, right? Then, of course, when you add details, you have to show me that it's robust, but you want something that actually works in this case, right? I think. I mean, since you are not playing with math, you are playing with the life of people, right? So, I mean, you can tell me, oh, but perhaps R naught is 1.9, but do you believe that? I mean, that you can? No, so. So I'm not convinced by that document, right? I mean, what is hard about epidemiology is that it's something where the behavior of people, I mean, you have parameters here, right? You have R naught, but R naught is an integration or an average over people behavior, right? And people behavior depend on what they know, right? So your behavior will depend on the fact that you know the SIR model, right? Which is something crazy if you think about it, but that's exactly why it's hard. So your behavior depends on what you know about the disease and what you do in response to that. Questions? And of course, here we are, I mean, we are taking a huge amount of information and details about how the virus spread, what are the form of transmission, sort of, and take all of these and putting together in one number, which is R0, R naught, right? Of course, there is a huge complexity there, which one can try to disentangle. Any other question? So I didn't mean to sort of depress you with all of this. I mean, I know that the moment we are living is not, even in respect to a few weeks ago, at least in Italy, is not particularly, I don't know, doesn't allow for much optimism in the short term, at least. But yeah.
I have a question.
Yes.
What are your predictions for December about the COVID here in Italy or here in Trieste? Because all the guys say that maybe we will be closed in December. And
Yeah. So I mean, I particularly feel for you and Jonathan and also Anna, because like you two are closed in a rooms for 2 weeks and you have the perspective of being for the next months, and you are in you would like to come, and it seems that the becoming slow. So I mean, I'm sorry that you are in these situations now. I honestly don't know. I mean, in the sense that, I mean, I don't think that the numbers are gonna change by themselves, right? And we are not in, if you look at, okay, so these, as you all know, these intersect very much with the politics, right? So what political decisions you take, and I mean, we come from different countries, and so we have experience of how different countries have dealt with the pandemics or not have dealt, and we saw how that affected the spread. So my feeling is that, I mean, well, there is this, plus there is the fact that everything you do is not having any effect, if not 2 weeks after you have done it, right? And the 2 weeks comes from the fact that the time scale we have rescaled at gamma is on the order of 2 weeks, right? So you do anything to your system and you see it only after 2 weeks at least. Right? So if your question is, do I believe that anything is going to improve in 2 weeks from now? No, because we have done like sort of major things in the last 2 weeks in Italy, right? In the sense, I don't think that there was any measure which is likely to have changed the course of epidemics. Are things going to improve in the next 4 weeks? It depends on what we do tomorrow, right? And since the scenario is very hectic in some sense, so it's changing very fast. Yes, it's possible that things in December are going to be much better. Yes. This is, I think, what is the reality we are facing, right? Then, I mean, honestly, I don't know. I mean, there are many things that can change. I don't think, I mean, it's very hard to make predictions on the time scale of December, right? Because it really depends on choices that nobody knows what they are, right? It depends on political equilibria, which are hard to assess, I think. And political, not in the bad sense necessarily, right? Is that there are, of course, conflicting interests, and it's normal that, I mean, and they are conflicting for a reason. So, I don't know. I don't think we should expect that in December it's going to be like it was July here. That's for sure. Yeah. So I think that the sort of for you, I think that I mean, it's likely that we are going to move more and more online, but I think that is a reasonable expectations that in this sort of starting from the spring, let's say, which is not very close, we are going to be, I mean, in a much better situation. I guess, I hope. Yeah, but don't trust my word. I mean, on this, I don't have any particular, I don't have access to a deeper reality than you have, right? So it's just my opinion.
Okay.
Yeah. So when is your 2 weeks quarantine period finishing?
I think that it's Sunday, maybe.
Okay. Okay. And Anna, do you have any? No. Nothing. Okay. Yeah, I think it's, I mean, realistically, it's hard that things are gonna move soon. I don't know, but it's the geopolitics. So. Good. Any other question, comments? Well, there was an insect that fell. Well, anyway. Any other question, comments? Well, next Monday is an official holiday at ICTP, so we are not going to have the lecture in class. So if we will be allowed to move Ivan and Jonathan, I mean, use it to visit Trieste, since you're going to be out of the quarantine. So I think it's better if we move the Zoom on Tuesday or on Wednesday. So I'll try to find a time which is good for both diploma students and PCS students, and it's going to be in the afternoon, so there is no time zone issue. Probably Tuesday it's very busy for PCS students, so well, I'll communicate with you what is a good time for the Zoom, okay? But we will meet again next week. Great. Yes. Are there other questions? I mean, use also Slack if you have questions which are more, which are easier. And well, don't hesitate to get in touch for any question, issue, comments, etc. Okay. Well. Well, I have the feeling that I have to say something hopeful at this moment. So let me say that I hope to see you in person soon, however it goes. Okay. See you
Bye.
soon. Bye bye. Thanks.
Bye.
Bye.